up next, we have Melchior Edelman. Melchior is the Chief Growth Officer at Quantum Bridge, and he will be presenting to us the road towards a quantum internet. Melchior used to be a member of the programming committee, and we are happy to see him back on stage today. Welcome, Melchior.
Thanks. Yeah, let's find the clicker. Yeah, thanks. So first, as a small introduction about Quantum Bridge, I assume most of you have not heard about it yet. It's a small startup from Canada, headquartered in Toronto. And Quantum Bridge focuses on two things. One is more our research and R&D, which is in the field of building a quantum repeater. That's still pretty, let's say, foundational work. So there's not a quantum repeater yet, right? And the second thing is we have built a solution for securely distributing symmetric key material within a network. Previously, I was with Juniper. I led the quantum initiatives in Juniper. So I started looking into the quantum space around 2018, basically figuring out what it means for us as classical network engineers, what is coming and where should we look at. I don't have a physics background, so my view is purely from how can we use this technology and in classical networking. So you might have heard indeed, let's say, a lot about rumors and stories about the quantum internet. There is no quantum internet yet. As you probably know, there's not even a really working quantum computer. But at one point, obviously, it is expected that we might have quantum computers. I think NVIDIA CEO predicted 20 years, right? So it's somewhere between 10 and 30 years. There are already quantum computers, but with very small number of qubits, quantum bits. But at one point, a quantum computer will exist, and so a quantum network will probably need to be built. And that's going to look a little bit different than classical networks, how we are used to, right? So at least for now, you would always still need a classical network next to a quantum network. And a quantum network is links, dark fibers, or specific wavelengths, where you send polarized photons over. And these polarized photons we call qubits. But the big difference is, if you compare to classical networking, you can, in classical networking, amplify light, right? We all know probably amplifiers in CWM and DWM networking. You cannot do that in quantum networking, at least not where we currently stand, because the problem is you change the properties of this qubit if you try to amplify it. So that's a limitation currently for some systems and applications that are already available that use quantum properties, that you can only span like 100, 150 kilometers, right, because of this limitation. But before we go into some of the things, how to get to this quantum internet, there are some application scenarios where a quantum computer is much more powerful than a classical computer, right? For example, factoring of numbers, right? And classical computer is very good at multiplying numbers, right? But factoring numbers is something which is really hard for a classical computer. And that is where a quantum computer is expected to be very good at. So at one point, if you start building these, let's say, quantum networks, you see a few of the use cases here. And there's one application, we'll look into that in a bit, which is already available. That's called quantum key distribution. But there are expectations that at one point you can actually do more with these quantum computers, like blind computing. You can do sensing, very sensitive sensing you can do with quantum, but also clock synchronization, etc. There's an RFC also in IETF that describes a lot of these use cases. So I already mentioned a few words which maybe sound familiar or not, but the way how this quantum network works is much different than what we're used to. Basically, we're building between, let's say, routers. We're building entanglement, and we'll get to what entanglement is, in order to send data across this network. That is much, you could sort of compare it to, let's say, link state routing, right? Where you route between nodes. However, as I mentioned, you cannot let's say, amplify or interfere these polarized photons, so you change the state, right? So currently, if you want to build a network as you see it here on the slide, you need to always go from optical to electrical to optical again. Basically what we're doing in classical networking. The end goal obviously would be to be able to send these qubits from point A to point B, wherever that is in the world. But let's take first one step back. I mentioned qubit. We all know classical bits, right? They're always a 0 or a 1. In quantum, it's a bit different. In quantum, we have qubits, quantum bits. And the interesting thing here is that if you bring them into a superposition, then the bits are 0 and 1 at the same time, until the point that you observe this photon, this qubit. Then it will collapse into a 0 or a 1. You can sort of compare it with if I would throw a football and give it a spin, you only know if what you're seeing, what is in front of you, if you catch it, right? But then the movement stops. So then the qubit collapses into a 0 or a 1. You either see the logo or not, right? Depending on at which point you catch the football. So what is a superposition? If you compare it to audio, what you hear, if you're listening to music, for example, is a combination or aggregation of different waves, right? But you hear only the result, the combined wave. And that is sort of how a superposition of a qubit or this electron looks like. Where the difference is, again, that if you measure it, you do get which wave you see, the 0 or the 1. That's different, obviously, in audio. You cannot go back, let's say, re-engineer the original waves of which the combined result is. So in order to really start sort of moving data around, there's another pretty interesting aspect or property to these qubits. You can entangle them. In other words, if you have 2 of these qubits and I measure the one on the left side, then the other one on the right side will collapse into the opposite state in this example, right? So if you see qubit 1 and 2, if you measure 1 as red, then 2 will collapse into blue. And this is what is being referred to as the spooky action at a distance, because it doesn't matter how far you bring them away, right? You have to bring them really close to become entangled. And then if you teleport them or you send them to a different location and you do this measurement, then always the other one will collapse as well. And that's obviously a very interesting aspect if you think about some of the use cases we saw. For example, this clock synchronization, right? Because the entanglement breaks or the superposition stops at the moment that you measure one, the other one at the same time collapses as well. But also, this is exactly what happens if you would amplify one of these photons, then the photons collapse, right, into their 0 or 1. So this is also an interesting property for security, for example, right? Because if somebody now starts interfering with this fiber where you're sending these polarized photons, if you observe it, it collapses, right? So then the other side will know that there's no polarized photon received, or the original photon collapses as well. So you can detect that somebody's interfering with the communication, and that is something we cannot do in classical. I already mentioned things about measuring. There's a picture here from Single Quantum. They built photon detectors. This is also one of the challenges why this equipment is not really yet ready to be put in the data centers we're used to, because you need a lot of cooling for these photon detectors. They are not really that easily rack mountable, right? There are some who are getting close to that, but they're still pretty large, bulky machines. There are companies, startups working on bringing this technology into a smaller form factor. For example, what would be really interesting, obviously, at one point, if you could make the technology so small that it would fit into a transceiver, right? Where you then could combine potentially classical and quantum bits on the same fiber, because that is possible. If you have it on a different wavelength, that's fine, but just not amplify it again. So I mentioned actually the only application which is currently, let's say, commercially available from Toshiba, ID Quantique, there's quite a few of these QKD vendors, is quantum key distribution. And we'll look into how that works. There is a protocol that is called BB84, which is invented by Bennett and Brassard in 1984. That describes how you can use this polarization, these polarized photons, to transport data to another node. So we have Alice and Bob nodes, and it's always Alice sending the photons, and Bob has a photon detector, and so is, let's say, observing the photons. Between these nodes, you need, again, a dark fiber or a wavelength, and there is a separate data channel, because they also need to synchronize a lot of data. And so how it works, Alice starts sending these polarized photons. You see here with errors how she sends them. So let's say 0 degrees, 45 degrees, etc. And Bob measures these photons. And you see Bob should measure the same photons as the ones sent by Alice, right? And that is where if somebody interferes, the state changes. But as a security mechanism, they use a different base to measure the photons, right? So it's either a square or a rectangle where they push the photons through, so to say, before measurement. So the basis is different, and this is a random filter they're using. After that, you have results, and as you can see now the results differ, right? Because Bob didn't know which photons Alice originally sent, and you see that if the filter matches with the polarization of the photon, the result is as the original photon that was sent. However, if the filter doesn't match the polarization of the photon, then the result, the end result is different as well. So now as a next step, Alice and Bob exchange via this classical channel their filters. You can do that in basically unencrypted, that's fine, right? Because with the filters itself, you can do anything. And now if they overlay the filters and the results, you see that you're getting to a key. And this is very simplified how, let's say, some of these QKD protocols work. There's next to BB84, there's others as well, but this is, let's say, the classical one. And this is actually available, as I mentioned today. And because of this combination of the filters and the fact that if you measure a polarized photon that it collapses, the error rate will increase at Bob's side, right? If somebody starts interfering with this quantum channel. So this is, again, this is available. It is limited, right, in distance. That is challenges. Oh, the mic stops working now and then, I believe. So this is his limitation, and this is always point-to-point currently, right? So you need to have a set of Alice and Bob's per link that you want to would want to secure using that key material they produce. So now that we've seen this application, why would you even need this, right? You probably heard, as we mentioned at the beginning of the talk, there is a belief that a quantum computer that is able to successfully attack encryption as we're using it today is available somewhere in between the next 10 to 30 years. And I know physicists and experts have been saying that for the last 20 years, right? So we'll basically never know when it's available. However, there's other things like classical computers and MEM computing, which are catching up rapidly as well. So it could be at one point that the classical computer is even a bigger threat to security than a quantum computer. Why is a quantum computer a risk for security? What we're using in classical encryption for key exchange, Diffie-Hellman, and elliptic curve, those are vulnerable for what's called the Shor's algorithm. And Shor's algorithm is supposed to run on a quantum computer if it ever becomes available, and would then be able to successfully attack this key exchange. In other words, you can then get the key to decrypt the data. So that's basically what this slide is describing. So the asymmetric cryptography or asymmetric key exchange, that is the problem, right? The vulnerable protocols are RSA, Diffie-Hellman, elliptic curve, etc. So what we're using a lot in encryption today. The good news is that, or in key exchange, the good news is that the encryption itself, based on AES 256, is considered to be quantum safe, right? So the problem what we need to fix is the key exchange. So one of the solutions is symmetric key cryptography, right? So symmetric exchange of key material, but that's very hard to scale, right? Probably most of you know about how they do this with DNS servers. There's people flying around who manually roll over the key, right, during a key signing party. That works pretty well if you have a few DNS servers worldwide, but if you have thousands or 2,000 home workers, that doesn't really scale. So that is where this solution, for example, like QKD could play a role. But there's also other methods. We'll talk about them as well. But even if you believe a quantum computer will never exist, or will take even more time than this 30 years, legislation is simply going to force you at one point to take action and to start using a quantum-safe encryption or key exchange mechanism. The Trump administration withdraws some of these documents, but the Biden administration was pretty advanced already with some of these advisories from the White House directives, but also in other parts of the world. The BSI, for example, is the German Secret Service. They state it's advisable to use quantum-safe mechanisms in the very near future. A lot of these things are still advisories, but as we've seen typically that some of these advices obviously over time will go more into the legislative landscape. So at one point, you simply will have to comply to legislation, right? You can believe a quantum computer will never exist, but you cannot not believe in legislation. Same as with NCSC, right? NCSC expects that major commercial products and services will transition to quantum safe once NIST standards are available. And that refers specifically to post-quantum algorithms, because that is the second option next to quantum key distribution to use PQC, post-quantum cryptography, which is still based on mathematics, but it's with a much harder problem to solve, even for a quantum computer. So you also see that throughout the geography of the world, the advisories differ, right? The US follows NIST very much, obviously, and NIST advises PQC. But in Europe, there's a lot of developments in QKD, for example. So what is the impact of these algorithms? There's a lot of impact. If you look at the left side of the slide, you see a lot of protocols being mentioned that uses their own crypto stack, right? So they need upgrading at one point. And there's a lot of work already going on in IETF, right? For example, for SSH, there's already a draft that describes how to use a PQC algorithm in SSH, and same for IPsec, etc. The good thing is that a lot of these algorithms and mechanisms are supported by the ones you see on the right, like HTTP, the ones on the right, they don't need updating themselves because they rely on the left side, right? So if the foundations are solved, then things like HTTPS quick and DNS over HTTPS becomes quantum safe as well. But as you can imagine, there's quite a lot of work, right? Because standard in IETF takes a couple of years before it's done, it's written. Then the networking vendors, the Juniper, Cisco's, whoever of this world, they need to start doing the work and implement it. And then probably nobody wants to be the first to switch to one of these algorithms, right? We've been using elliptic curve Diffie-Hellman for probably, 20 years? Now, all of a sudden you should switch to a algorithm which is just a few years out and hasn't seen wide deployment yet. So that will take some time as well. So the third option is symmetric key establishment, which is all based on software. It gives you the same result as QKD does, so you get two keys in different locations, but without exchanging the key over the wire. So there's no key exchange being done. That makes it quantum safe as well, right? Because if there's no attack vector, sorry, I can't read it. Slow down, oh, sorry. Okay, so there's no attack vector in a symmetric key exchange or distribution mechanism. And then the clicker stopped working. Ah, there we are. So this is a small idea of how, let's say, classical networking vendors get to becoming quantum safe. Some might expect that now that NIST has published these standards, which is the FIPS 203, 4, and 5, which is the PQC algorithms, that within reasonable time you will have a PQC algorithm, right? But if you look at these steps, and I'm not a coder myself, but there's a lot of stuff that needs to be updated, right? Both on the box, like TPMs and other modules that might not even support these PQC algorithms or might not support the larger key sizes. And then there's the work on the kernel, and if you have the kernel modules done, then you can update the crypto libraries. So before you can use these PQC algorithms in IPsec or SSH, etc., we're still a few years out. But there's also options to mix, for example, classical and PQC, right? As I mentioned, it would probably not be smart to already 100% fully switch to a PQC algorithm. Why? Because we haven't seen large deployments yet. There isn't much experience yet, so there could be implementation errors, there could be new attack vectors that appear. For example, one of the NIST finalists in the final round for a post-quantum algorithm was supposed to be a quantum safe. However, somebody with a laptop was able to, so a classical computer, was able to successfully attack it in 45 minutes. Right, so now you can have an algorithm that is quantum safe, but not classical safe. So it could be very interesting to start mixing multiple key exchange mechanisms, like for example RFC 9370, that describes mixing classical elliptic curve Diffie-Hellman with a PQC algorithm. Also on the signature authentication side, there is a draft that describes to use PQC algorithms to make them quantum safe, and this is RFC 8784, which is pretty well implemented now by the majority of networking vendors. This describes how you can supplement elliptic curve Diffie-Hellman with external key material. So you're still using the trusted, well-known, certified, etc. elliptic curve Diffie-Hellman in IPsec, but you now supplement that with external key material. In other words, if at one point this quantum computer becomes available, it can still not attack and let's say discover the key, because a part of the key is retrieved from an external mechanism. In other words, if you would use RFC 8784, you're considered to be classical safe because you're still using elliptic curve Diffie-Hellman, and you're quantum safe because you supplement with out-of-band key material. So let's see how that works. How can we use that key material in this case, in an example in IPsec? What RFC 8784 describes is that you supplement the IKE v2 negotiation with this external key material. In the top of the slide, we have two boxes. These are our QKD boxes, Alice and Bob. And again, Alice sends these photons to Bob, and out of that they construct a key. And we have two firewalls running a code base that supports RFC 8784. And now, if they want to use a quantum safe, let's say out-of-band key, if you configure that, the PVK, the post-quantum key, then the first step is to send a message in the IKE negotiation from Alice to Bob firewall. Hey, I want to use QKD keys in this case. If Bob has that functionality as well, it confirms that it indeed agrees to use that key material. Then a request is sent using a part that is also standardized, but then in ETSI, the ETSI 014 QKD REST API. It sends a call to that QKD box on Alice's side, requesting a key and a key ID. If it receives it, it installs the key into the crypto engine and sends the key ID to Bob. And now Bob can use that key ID to, on Bob's side, also request the key. Hopefully it receives the same key. Installs that key, receives the key, installs it in the crypto engine, and acknowledges that it's using the key with that key ID. So now you have both elliptic curve Diffie-Hellman exchange keys, and you're using external key material. And now we have what we call quantum safe IPsec connection. As I mentioned, this is standardized, RFC 8784. Many network vendors have done this work already. And there's quite a few solutions available that use this ETSI REST API. There's also the skipped version, which is the Cisco protocol, which some QKD vendors have implemented as well. So what about MACsec? The good news is that MACsec on itself is quantum safe because MACsec doesn't give you a mechanism for asymmetric key exchange, right? In MACsec, you configure the key on both sides and that's it. There's no key rollover, no key exchange. And MACsec uses AES 256, again, which is considered to be quantum safe. So there's no attack vector on itself in MACsec. So one could say if you never change the key, you are quantum safe, but never changing the key goes into many other security principles, right? What a lot of vendors did is they came up with a mechanism to out-of-band distribute this key ID, because obviously you can still use that etc REST API to request the key on both sides from QKD, use that in the box, but now you need to find a mechanism to exchange the key ID. There are vendors who have implemented this, who have code available, but it's proprietary, right? So you cannot run MACsec between your Nokia and your Juniper box. MACsec with quantum safe, I mean. So this is something that still needs to be standardized. So if somebody's interested in picking that up with IEEE, where MACsec is standardized, then please do so. It works more or less the same. QKD in MACsec. This is an example how the Juniper implementation works. So again, we have our LSMBOP QKD boxes, and we have two routers in this case. And between the QKD boxes, again, the quantum channel, the dark fiber, and the synchronization channel. And between the routers, we have our classical MACsec link, right? Nothing different there as you're used to how MACsec works. So again, in this case, it's a script that runs on the box because it's not part of Junos yet. That uses, again, the etc 014 REST API to pull a key from LSQKD. Once it receives that key and key ID, you put the key, in this case, into the configuration. And Juniper uses LDP to send that key ID to the other router. Now the other router can use the key ID to request the key as well. It receives the key, installs it, and the world is quantum safe. The interesting thing here is now that previously, if you would want to roll over a key, obviously in MACsec, you would need to coordinate with the other side and need to either send the key via WhatsApp or email or whatever. Now we have a mechanism that can help you roll over the key, even if you would want to every minute, for example. I don't know if that's practically the most handy thing to do, but you could roll over key automatically now. So what is the right way forward? As we said, switching to PQC 100% might not be wise. There are some implementations already available from both hardware vendors and software vendors. However, some of them now will need to change their implementation now that NIST has standardized the PQC algorithms. So that might not be handy yet because it's pretty well expected that we might see, for example, flaws in implementation or maybe even new attack vectors as well. Do nothing could be an option, but then you need to think about what is the value of my data in, let's say, 10, 20, 30 years, right? Because everybody knows that store and decrypt later attacks, as they are called, are happening, right? Where some entities already store data with the intention to decrypt it later. For example, I always joke the number of my bank account, nobody cares in 10 years, right? But where the US has its missile silos, it's probably still pretty interesting, right? Because they're not probably being moved in 10 years. So it depends on what is the value of your data in 10 years. For now, the advice would be to go for a hybrid approach, right? And if you read all these documents from NSA, from BSI, from all the secret services and other agencies, they basically all say mix classical with either PQC or with this out-of-band key material. So if we bring that back to the quantum internet, the first steps are there. I mean, there are already connections possible, short distance, as I mentioned, 100 kilometers, maybe a little bit more. But what we see from these implementations, that there's a lot of learnings there, right? So, for example, on the standardization perspective, you can currently not have, for example, 2 QKD boxes from different vendors talk to each other. Or there's not even standardized how indeed this key ID should be exchanged in MACsec. And so there's a lot of learnings there, a lot of standardization to be done. Before we will really see a quantum internet or quantum network starting to appear, we need these quantum repeaters. That is at least 5 years out. But the time is now to start preparing for this, let's say, at least quantum safe future, right? It's hard to prepare for the quantum network or quantum internet, but it is expected that at one point customers or legislation starts simply forcing you to at least encrypt data in a quantum safe fashion. And there's a lot of work to be done in ITF. For example, the QRNG, the Quantum Internet Research Group, there is a proposal to start a symmetric key distribution working group in ITF as well, to specifically focus on software to do symmetric key exchange. And there's post-quantum working groups as well. And as I mentioned in ETSI, they're working on these interfaces and orchestrators, etc. And IEEE, obviously, for MACSEC. And that's it. Yeah, I went a bit too fast. I see that now as well. Sorry about that.
Conversations around it. And we have some questions online. Folks in the room, if you have questions, please line up on the microphone.
Hey, Sergey.
Remember to introduce yourself, please. Good.
Hey, Stephen with incredibly complex Polish surname. I'll try to read it out. Josh is wondering, does Quantum Bridge have any leaf proof of concept there for demonstration for quantum key distribution, similar to what Toshiba, BT, and Ernst & Young are doing?
Yeah, for sure. Yeah, so we've actually built a proof of concept a couple of months ago for the system banks to demonstrate how you can build these quantum safe IP connectors. So yeah, so if there's interest, we can definitely demo that. Sure. Yeah.
Thank you.
Hi, Scott Johnson, Spacely Packets. Last year, Google and D-Wave collaborated to demonstrate that there is a great possibility that a quantum entanglement is actually a quantum wormhole, and that this could potentially be exploited to create a faster than light layer 1, or at least a mechanism to achieve a layer 1 with free space optical. If you can make a large enough aperture between the entangled particles, possibly with something like a single ring of graphene or something along those lines. I was wondering, that was with an older version of D-Wave's quantum annealed solution, and they've now released, I believe, a 5,000 qubit unit. I was wondering if you had any opinions on that both being a real application of quantum computing and the possibility of that mechanism to allow a layer 1.
Good question, which I don't know the answer to. I'm not, as I said, I'm not a physicist myself, right? I look more at how can we apply some of these things the physicists are working on in networking. So sorry, I don't know the answer to your question.
No problem.
But great question.
Randy and Cisco, great talk.
Thanks.
Very interesting. Given the initial deployments of the QKD, if you would summarize the key challenges that you talked about, the lessons learned, would you share some of those challenges that you are aware of?
Yeah, sure. Yeah, so I think the biggest challenge, as I mentioned, is obviously the distance limitation, right? With these 100, 150 kilometers, you can span the metro of a large city, right? But you cannot span Amsterdam to New York without trusted nodes, right? So where you go from optical to electrical to optical, and that is obviously a challenge, technically. So the second challenge is that you need a pair of these boxes per link, right? So if you have a large network, it becomes pretty complex. You need a lot of boxes. Plus the fact that these boxes are currently still pretty expensive, right? The technology is there, but there's no wide deployments yet. So it's still really expensive. So the business case currently only works for very few agencies or large companies. And again, only in very limited capacity. So I would say that those are the biggest challenges for QKD currently. Yeah.
I mean, thank you. And you would expect definitely a lot more acceptance from the governments, the military, do you see the commercial companies kind of more actively looking into this type of a deployment? If they are, what are their complaints, their challenges?
Yeah, yeah, there is a lot of interest, especially also when I was still in Juniper. We did a lot of POCs, proof of concepts, with QKD vendors and commercial entities. Indeed, a lot of, for example, finance, banking, healthcare, all those who have this very sensitive data. So there's huge interest there. But in many cases, indeed, the discussion sort of stopped when it came to pricing of the solution, or indeed the usability. So where QKD currently stands, it is usable in some use cases, but a lot of things still need to happen, right? If these quantum repeaters materializes, then the use case obviously becomes much more interesting and appealing. And also, as I said, some of these companies are working to bring the technology to the size of a transceiver. That's going to be a game changer as well. But it's early stage for the technology, right? I mean, a lot of these companies who are building QKD currently, they, for example, have here how we build classical networks, right? So they need to learn a lot in that space as well, how to catch up, how do you even monitor the solution, right? Does it have, can it do streaming telemetry, or does it have SNMP, for example, stuff like that. So there's still a lot to be done before we will see wide commercial adoption. But at one point, and that is why I focused on this legislation, at one point you cannot wait anymore, you need to start acting. And I don't know if QKD is the answer, or PQC, or Symmetric. They all serve their own purpose, right? For example, how small QKD is going to be doesn't matter for me as a home worker and somebody who travels a lot, right? I'm not going to carry a QKD box in the plane. Right, so I'll probably be using PQC, maybe combined with a Symmetric key solution, because that is software I could run on my laptop. But for DCI, within the metro, I can imagine a situation where you have QKD, right? So it depends a lot on the use case.
Thank you.
Sure.
Is there time for another one? Anybody else? Can I, one more question. And you and I talked a little bit about the error correction, error detection issues that's kind of common. So what are you hearing how to address that problem from the industry perspective?
Yeah, again, a good point. I'm not a physicist. I'm not on that side, so I don't have the answer how to solve that. Sorry.
Oh, no problem. Thank you.
Sure. Uh-oh, another tough question.
Scott Johnson again, Spacely Packets. Pursuant to the topic of quantum safe algorithms, it is my understanding that these algorithms are designed to be impermeable to the capabilities of today's quantum computers. It is understood that limited functionality is, specific functionality is available from quantum computing today, and that these algorithms are designed around jobs that the present quantum computers are not very good at. What thought has been placed into the evolution of quantum computing as relates to these algorithms and their deprecation or not deprecation based on that?
Yeah, no, that's an excellent question. And that is why I think a lot of these agencies indeed also suggest not to just switch to PQC, right? Because it could very well be that this quantum computer, once it exists, is even more powerful, or could also attack these PQC algorithms successfully. So the challenge is, if you switch to PQC now, you have no idea if that still holds in the future, right? So that is indeed why it would be wise, even if you would switch to PQC, to still supplement with additional key material, which is distributed out of band, whether that's QKD or PQC, DSKE, so Symmetric key, or even by trusted couriers. Right, having for highly secure data transfers, there is a reason why the US Air Force, for example, only trusts on physical couriers, right? They've never trusted asymmetric cryptography at all, right? So they do this physical key delivery with people flying around, right? Because that is still the most trusted solution. There is no attack vector for a classical or quantum computer. So yeah, so it could very well be that even these PQC algorithms might prove to be vulnerable in the future.
All right.
Thank you very much.
That was great, Malkir. Thanks so much.
Thank you.
Hand for Malcolm.